Network Infrastructure and Design, Network Models, the TCP/IP model. Whereas in the previous module, we talked about the OSI model, a mostly theoretical model that's in use in computer networks. In this module, we're going to talk about perhaps what is considered to be one of the most common, or at least the most widely used model, the TCP/IP model. Now, while it's important that we memorize and familiarize ourselves with the OSI model, it's also really important that we understand this TCP/IP model and the differences between it and the OSI model. As technicians and administrators, it's really important that we're familiar with each layer, as well as how data transfers between all of these layers, and how all the protocols that are used in TCP/IP relate to one another and in the layers. So, the objectives of this module are first to explain the purpose and depth of the TCP/IP model and to compare it in some ways with the OSI model. We're also going to talk about what data encapsulation and fragmentation are. These are really key to how large amounts of data are able to be transmitted and transferred over the internet, the largest network in the world. And then we're going to talk about the 4 layers of the TCP/IP model, beginning with the 4th one, and then the 3rd, the 2nd, and the 1st. Finally, we're going to talk about protocol binding and something called an MTU Black Hole that doesn't really occur much anymore, but that Network Plus wants you to be familiar with. So, as mentioned before, the TCP/IP model is perhaps the most widely known or used networking model. It's another networking model that's most commonly defined using abstract layers, just like we had with the OSI model. Now, the entire purpose of this model is to allow for conceptualization of how a computer network functions in maintaining hardware and protocol interoperability. Also, it's commonly called the DoD model for the Department of Defense, which funded much of the research that went into it. TCP/IP was permanently activated in 1983, and it's been in use just about ever since. Now, it wasn't until 1985 that this model was actually commercially marketed, but it is now the preferred network standard for protocols and so on. Now, this means that using these 4 layers on this model, the bottom being the network interface layer, the internet layer, the transport layer, and then finally the application layer. And if you know or remember the OSI model, you'll see that there is some resemblance. Understanding this model and understanding how data flows is actually how the entire world is allowed to communicate and connect to the network. So this is necessary for every computer in the world that is currently using the internet, and for the most part that's on any network. We might find other smaller, lesser known protocols that do operate outside of this, but I think you would be hard-pressed in today's day and age to see that. So technicians and engineers will probably sit and talk about technology's implementation of these 2 models for hours on end. And the reason is because there's quite a bit of history and brilliant thinking that went into the creation of both of them. The TCP/IP model was, in fact, created before the OSI model, and it still makes it easier to represent how communication and network-related protocols are defined and relate to one another. However, it's still more common to hear technicians and administrators use the OSI model when they're troubleshooting or referencing networking devices. And there are many similarities between the 2 models. The first similarity is the obvious use of the layers to describe the functions of these communication systems. Although in TCP/IP we have 4, whereas in OSI, as you recall, we have 7. Some of them even have similar names, as you can see from application and transport, and then we see network or internet and network interface, which is very much like physical. In some ways, some people consider the TCP/IP model to be a smaller version of the OSI model. However, this leads to some misconceptions about the position of relationships of certain protocols within the OSI model. Because these are 2 very different designs and they have different purposes, there are some recognizable similarities, but they're still, at their core, different. So the purpose of this OSI model was an attempt to simplify and standardize networking. TCP/IP's original purpose, as opposed to the OSI, is more attempting to sort out the internet protocols into comprehensive groups according to their functions of the scope and the sort of network that's involved. Now, one of the similarities between the two models is they both have interchangeable network and transport layers. Also, each layer of the OSI model directly correlates with the TCP/IP model. Now here you can see the application layer, the presentation layer, and the session layer of the OSI model correspond to what we know as the application layer of the TCP/IP stack. This means that everything in the OSI model that fell into application, presentation, and session are actually done in the application support block. Next, the transport layer of the OSI model corresponds directly to the transport layer of the TCP/IP model, the network layer of OSI with the internet layer of TCP/IP, and that is easy to remember since internet is really short for like internetworking. And the data link and physical layers of the OSI model correspond directly to the network interface layer of the TCP/IP. Now, some of these correlations, it should be mentioned, aren't precise and exact. They're sort of approximations, and that's because they are two very different models, and therefore they were created differently and weren't necessarily created with the one or the other in mind. That being said, TCP/IP and OSI were built with knowledge of one another, and so we do see this overlap. Now, the TCP/IP model outlines and defines the methods data is going to flow in a communication system. It does this by assigning each layer in the stack specific functions to perform on the data. And ultimately, each layer is completely independent of all the other layers and more or less is unaware of the other layers. For instance, the topmost layer, the application layer, is going to perform its operations if the processes on the communicating systems are directly connected to each other by some sort of information pipe. The operations that allow for the next layer, the transport layer, to transmit data between the host computers is actually found in the protocols of lower layers. And from there on, each data layer will complete its specified actions to the data and then encapsulate the data, where it's then passed down the stack. In the opposite direction, when data is traveling back up the stack, and we saw the same thing with OSI model, the data is then de-encapsulated. So when it's going down, we call that being encapsulated. And when it's going back up, we call it de-encapsulated. So we really need to understand how all of this works together in order to get a really strong picture of TCP/IP and be able to speak about the layers in general. So let's talk about encapsulation. Each layer is responsible for only the specific data defined at that layer, as we've said. Now, these layers are going to receive the data package from the layer above it when sending, and the layer below it when receiving. This makes sense. If I'm receiving data, it's going up, so the data is coming from below, and if I'm sending, it's going down, from the application down to the networking interface. Now, when it receives this package, each layer is going to add its own packaging, which is called a header. This header is used by the corresponding layer at the receiving side for specific purposes. The exact purpose is really going to depend on the layer in question. But this header is going to be added to the beginning of the data so that it is the first thing received by the receiving layer. That way, each layer on the receiving end can then remove that header, perform its operations, and then pass the remaining data up the stack, up the TCP/IP model. On the lowest layer, a footer is also going to be added. And this is going to add to the frame by adding more supplemental information. This extra data at the end of the data package is going to assist the receiving end on ensuring that the data was received completely and undamaged. This footer is also what's called an FCS, or a frame check sequence. And as the name implies, it is going to check to make sure the data was received correctly. Now, on the receiving end, this process is reversed by what's called de-encapsulation. In other words, the data is received at each layer and the headers are removed to allow the data to perform the related tasks, where finally the data is received by the application layer, and then the resulting data is delivered to whatever the requested application was. Now, just like with the OSI model, and we'll talk about later, this application layer doesn't mean the actual application itself. It's simply the layer that provides access to the information from an application. Now, just like the OSI model, there are a few mnemonic devices that can be used to help in remembering these layers in order. And the one that I use the most, going from the top down, is called All Things in Networking. Again, that's application, all, transport, things, internet, in, network interface, networking. So now we have a better understanding of how the data is going to proceed from layer to layer through encapsulation, going down from application to transport to internet to network interface, right? And then through de-encapsulation, which goes the opposite way. Let's take a closer look at these layers, starting with the topmost layer, the application layer. So here on the application layer, much like the application layer of the OSI model, we find what's considered the highest level protocols. Higher level meaning these protocols such as SMTP, FTP, and so on. These protocols are not necessarily concerned with the method by which the data arrives at its destination, but simply that it just arrives, period. Here in the application layer, we also provide the functions that relate to the presentation and the session layers of the OSI model, as we've already pointed out. It does this typically through the use of what are called libraries, which are collections of behavioral implementations that can be utilized and called upon by services that are unrelated. So this means that the application layer of the TCP/IP model encodes the data and performs any encryption and compression that's necessary, as well as initiating and maintaining the connection or the session. As we can see here, these are just some of the protocols that we find at the application layer. We can also further group some of these applications based on the specific type of function that they provide. For instance, if we're looking at protocols that are dedicated to transferring files such as FTP or TFTP, which if you recall is the trivial FTP. Then there are also protocols that can be categorized by supporting services. So some of those are going to be, for instance, DNS, the domain name service, and SNMP, which is for management purposes, or even BootP or the Bootstrap protocol. Now, just like the OSI model's application layer, this TCP/IP application layer is responsible for process-to-process level data communication. This means that the application itself doesn't necessarily reside on this layer. What it more means is that it defines what the application or what type of application can be utilized depending on the protocol. So for example, SMTP specifies that outgoing mail communication with the mail or exchange server, and IMAP specifies the incoming mail communication with the mail server. Also, remember that only those applications that are network relatable are going to be managed at this layer, not necessarily all application. So this layer's role is more towards software applications and protocols and their interaction with the user. And it's not as concerned with the formatting or transmitting the data across the media. For that, we have to move lower down into the model and get to the transport layer. Now, on the transport layer of the TCP/IP model, we have two main protocols that we need to be familiar with. First, we have the Transmission Control Protocol, or TCP, and the second is the User Datagram Protocol, or UDP. Let me just write those out here so that you can see what these stand for. Again, now on this layer, three things are going on. Data verification, error checking, and flow control. Now, our two heavy-hitting protocols are done in very different ways. So TCP/IP, as we've talked about in the past, is what we call connection-oriented, which means there's a guaranteed delivery, whereas UDP is connectionless, which means it's just a best effort delivery. UDP doesn't have any means of error checking. That's one of TCP's areas of expertise. So to put TCP and UDP in perspective, I've always thought about it as if, say, a grade school teacher needs to send a note to a student's parent because the student hadn't turned in their homework for more than a week. Now, the teacher can send the note one of two ways. The first is through UDP, or the uninterested, doubtful preteen. Now, this UDP is certainly going to make it home as quickly as possible, but whether the message gets sent to the parent or not really isn't UDP's biggest concern. Getting there quickly is. So UDP is going to have you that quick, but not necessarily guaranteed. Now, meanwhile, the other method, TCP, or teacher calls parent, this is the way the teacher has a guaranteed delivery of the message. But if parents aren't home, the message cannot be delivered, or something happens during the communication process, TCP will wait and attempt to send the message again. So, whereas UDP is quick, TCP is guaranteed. And so that's sort of the give and take there. Now, while our story is a generalization, it really touches on the two most important characteristics of these protocols. Now, there are a few other specifics about TCP that are really worth mentioning. Firstly, and most importantly, we have reliability, like we just mentioned. How it accomplishes this is TCP assigns sequence numbers to each segment of data, and the receiving end looks for these sequence numbers and sends what's called an ACK, or acknowledgement message, which is something important that you do want to be familiar with. And you might also see that as a SYN ACK, which is the synchronization. And that ACK message is sent when the data is successfully received. Now, if the sending transport layer doesn't receive the ACK or acknowledgement message, then it's going to retransmit the lost segment. Secondly, we have data flow control, which is we've already mentioned. This is important as networking devices are not always going to operate at the same speeds, and without flow control, slower devices might be overrun with data, causing network downtime. Thirdly, we have something called segmentation, and segmentation occurs at this layer, taking the tedious task away from the application layer of sectioning the data into pieces, or segments. These segments can then get sent to the next layer below to be prepared for transmittal across the media. So the final consideration for TCP is, in order for an application to be able to utilize this protocol, a connection between port numbers has to be established. The devices try to create this session using a combination of an IP address and a port number. Now, this combination is called a socket. In the future modules, we're going to look at referencing TCP and UDP, as well as going a bit more further into explaining how they function and interact with different protocols. But what you see here is the IP address on a specific port number. So we know, based on this port number, what the connection is trying to attempt. And whether or not it's TCP or UDP, we know whether it's connection-oriented or connectionless. The internet layer of the TCP IP model corresponds directly to the network layer of the OSI model. Now, the data terminology on this layer, as I think we discussed when we talked about the OSI model, is a datagram. Now, as the internet layer relates directly to the network layer, which, if you recall, was layer 3, we can a little more easily understand a few things that happen on this layer. First, it tells us that this layer is responsible for routing. If you recall, layer 3 devices for OSI are routers. This means that it ensures the typically fastest and best path from the source to the destination. This layer is also responsible for data addressing. And if you recall, with data addressing, we're dealing with the second part of TCP IP, which is the Internet Protocol, aptly named since it is on the Internet layer. And the Internet Protocol is responsible for a couple main functions. The first of those functions is what we call fragmentation. It's important for us to understand something called MTUs, which are maximum transmission units. so that we know why fragmentation has to occur. Now, the MTU is the term, as the name implies, that's used to define the largest size of increment of data in bytes that can pass through the given network device, such as a router. Now, often data is going to need to pass through networks with MTUs that are less than the MTU listed on that device. Generally, even not just match to, but the lower it is, the more it's preferred, because then we can make sure that it's not going to have a problem. So network devices are going to send and receive messages or responses to datagrams that are larger than the device's MTU. In these instances, when there is a datagram that's larger than the MTU of a device, the transmitting internet layer fragments the data, or the datagram, and then tries to resend it in smaller and more easily manageable blocks. So once the data is fragmented enough to pass through the remaining devices, the receiving end's internet layer then pieces together those fragments during the reassembly process. Now, in the header of those fragmented datagrams, if we go back just a bit, you'll see right here, the header, there's a specific field that's set aside for what we call 3 flag bits. The first flag bit is reserved and should always be 0. The second is the don't fragment, or the DF bit. Now, either this bit is off, or 0, which means fragment this datagram, or on, meaning don't fragment this datagram. The third flag bit is the more fragments bit, MF. And when this is on, it means that there are more fragments on the way. And finally, when the MF flag is off, it means there are no more fragments to be sent, as you can see right here. And that there were never any fragments to send. So as we see here, our initial datagram that we wanted to transmit had an MTU that was too large to send. It was 2500. And it was too large, therefore, to go through router B. And so then we fragmented this datagram and added those bits to the headers of the fragments. So that's how this all works, and that's why fragmenting is so important. Now let's take a look at a networking problem that used to plague network engineers and technicians that has to do with MTUs for some time. And this is also something that's specifically called for on the Network Plus exam. Now, a black hole router is the name given to a situation where a datagram is sent with an MTU that's greater than the MTU of the receiving device, as we can see here. Now, when the destination device is unable to receive the IP datagram, it's supposed to send a specific ICMP response that notifies the transmitting station that there's an MTU mismatch. This can be due to a variety of reasons, one of which could be as simple as a firewall that's blocking the ICMP response. And by the way, when we talk about ICMP, we're really talking about the ping utility as well. Now, in these cases, this is called a black hole because of the disappearance of datagrams. Basically, as you can see, I'm sending the data gets here. The device, the router here, says, wait a minute, I can't fit that 2500 MTU through my 1500, sends a response, but for some reason the response hits this firewall and doesn't make it back to the router, and so the data is lost into this black hole. Now, this is called a black hole because this datagram disappears as if it were sucked into a black hole. Now, there are some ways to detect or find this MTU black hole, and one of the best ways is to use the ping utility and specify a syntax that sets the MTU of the ICMP echo request, meaning you tell it, I want to ping with this much of an MTU, and so then we can see if the ping's not coming back. If it's coming back at one MTU and not another, then we know, oh, this is what's happening right here, and we can determine where the black hole is specifically occurring. Now, on the bottom of the TCP/IP stack is the network interface layer. Now, this layer is completely dedicated to the actual transfer of bits across the network medium. The network interface layer of the TCP/IP model directly correlates to the physical and the data link layer of the OSI model. Now, the data type we're going to be talking about on this layer are what we call frames, as opposed to datagrams. Now, the major functions that are performed on this layer, on the data link of the OSI model, are also occurring at this layer. So we're really talking about switching operations that occur on layer 2, which again is that data link layer. And so this is where we see switches operating. Which means that we're really dealing with MAC addresses. Okay? Now, a MAC address, again, is a 48-bit hexadecimal, universally unique identifier that's broken up into several parts. The first part of it is what we call the OUI, or the Organizational Unique Identifier. This basically says what company is sending out this device. And then we have the second part, which is the NIC specific. And then we have the second part, which is specific to that device itself. So this is the manufacturer, and this is for the device. You can literally go online, search for this part of the MAC address, and it'll tell you what company is creating this device. Now, the easiest way to find the MAC address in a Windows PC is by opening up the command prompt and using ipconfig all, which we've talked about in A+. This brings up the Internet Protocol information, the IP address, and it also brings up the MAC address or the physical address that's assigned to your NIC. So now that we've covered the MAC address it's really important to understand the parts of an Ethernet frame. And remember, we're talking about frames at this juncture. So the preamble of an Ethernet frame is made up of 7 bytes or 56 bits, and this serves as synchronization and gives the receiving station a heads up to stand by and look out for a signal that's coming. The next part is what we call the start of frame delimiter. The only purpose of this is to indicate the start of data. The next 2 parts are the source and destination MAC addresses. So the Ethernet frame, again, this is everything that's going over this Ethernet, over the network. We have the preamble. It says, hey, pay attention now. This that says, now I'm giving you some data. And then we have the destination and the source MAC addresses, so that way we know where it's coming from, who it's going to. And this takes up 96 bits. Or 12 bytes, because remember, this is 48 bits right here, so if we double that, that's going to be 96. And then the next type is what's called the frame type. This is 2 bytes that contain either the client protocol information or the number of bytes that are found in the data field, which happen to be the next part of the frame, which is the data. This field is going to be a certain number of bytes, and the amount of data is going to change with any given transmission. The maximum amount of data allowed in this field is 1500 bytes. We can't have more than that. Now, if this field is any less than 46 bytes, then we have to actually have something called a pad, which is actually just going to be used to fill in the rest of the data. And the final part of this Ethernet frame is called the FCS, or the frame check sequence, and this is used for cyclic redundancy check, which is also called CRC. This basically allows us to make sure that there are no errors in the data. Now, similar to the way that an algorithm is going to be used to ensure integrity of data, the CRC uses a mathematical algorithm, which sometimes we're going to refer to as hashing, which we'll talk a lot more about when we get to Security Plus. That's made before the data is sent, and then it is checked when it gets there. That way we can compare the 2 results bit for bit, and if the 2 numbers don't match, then we know the frame needs to be discarded. We assume there's been a transmission error, or that there was a data collision of some sort, and then we ask the data to be resent. Now, this layer, by the way, this network interface layer, is also responsible for the network access control, and some of the protocols that operate on this are what are called point-to-point protocols, ISDN, which is which we've talked about, also a type of network, and also DSL. So these are some of the things that exist at this, and this makes sense because, again, we're dealing with the physical bytes of data. So now that we've taken a look at each of the layers in the TCP/IP model, there's still a couple things that we still need to define. Now, we've discussed how some of the protocols that we've seen relate to the OSI model as well as the TCP/IP model. And we found that some of the protocols function much more smoothly when they're put into the context of an outline of one of these models. So the next definition I want to make sure to cover is something called protocol binding. This is when a network interface card receives an assigned protocol. It's considered binding that protocol to that NIC. So just as we learned how the data is going to be passed down from one layer to the next, it's very important that we have these protocols bound to the NIC. We can have multiple protocols actually bound to one network interface card. Now, of course, we can most easily recognize these when we're looking at the IPv4 and IPv6 configurations in our network connection properties or adapter settings in Windows. If, for instance, you use a specific protocol more than others, and you're confident in the stability of the connection, you can change the order of binding to potentially speed up your network, since what it basically does is it's going to give a list of each protocol that exists, and it's going to hit each protocol one after the other. So if there's one that you use more, you can set that at the top so it doesn't have as far to go. So as we can see here, we have several default protocols, and they're going to be tested in order for that available connection. And the first protocol that's found to have a matching active protocol on the receiving end is going to be the one we use. Now, while this might sound like a pretty decent method of doing things, it also opens your computer up to utilizing a lesser protocol, which is potentially going to give you a slower speed. So the graphical interface or properties menu for your network interface card is where you're going to be able to configure all of this stuff such as TCP/IP, DNS server assignment, DHCP, and so on and so forth. So after all of this, it's really important to understand that all of this organizing, categorizing, defining of these protocols, the assigning of rules and roles, all of this, the internet didn't just happen overnight. It's not even necessarily the way we did it on purpose. These standards and these models are going to continue to expand and change, and eventually we might even have a brand new model that we're going to have to learn about. But in the meantime, these models are here to stay, and they're going to remain really important, and especially in the future, you have to understand the historical roots of the network so you can be able to define not only how to go forward in the future, but also how to prepare yourself for our Network Plus exam. So let's just go back over everything we've talked about one last time. We covered in a lot of stuff here, right? First, we explained the purpose of the TCP/IP model, and we compared the TCP/IP model with the OSI model, remembering that the top three layers, if we look at this, if we do the 3, 2, 1, and then we look at 7, 6, 5, 4, right? 2 and 1, physical and data link, are going to go straight over here to that physical layer 1 of the TCP/IP model. Then the network layer is going to correspond directly to the internet layer. The transport layers are going to be the same. And session, presentation, and application all go over to the presentation layer in TCP/IP. We also talked about defining data encapsulation, and we walked through how fragmentation works on the internet layer. And the reason we need to do that is because of the maximum transmission unit. Finally, we talked about the fourth, third, second, and first layers of the TCP/IP model. And on each model, we outlined some of the important aspects of each layer, such as the application layer, which again is the way that the application is going to process all of this information. The transport layer, which is in charge of reliability. And it is where TCP, which is connection oriented, or UDP, which is connection less, live. And this is also going to deal with flow control and also segmentation. We looked at layer 2 as well, which is the internet layer, and the fragmentation that happens there. And network 1, the network interface layer, which is equivalent to all that physical stuff that we've talked about. We also looked at how the terminology changes. Remember, on layer 4, we're talking about data. On layer 3, we're dealing with segments. On layer 2, we're dealing with datagrams, also called packets. And we broke down then on layer 1 frames and an Ethernet frame and all the information that goes into that. Finally, we defined what an MTU black hole was, and we finished off everything by talking about protocol binding, which is binding certain protocols to specific NICs and in a delineated order.